Caroline, I'm going to record, okay? Hi everybody, we're going to be learning about vectors. This time, instead of being two-dimensional vectors, we're going to talk about how to apply vectors in 3 dimensions. So not just x and y, but x, y, and z. Here's your assignment down here. Make sure you're doing the reading. The reading is really going to help you master this skill. It's kind of a shorter lesson here. We're going to understand the 3-dimensional rectangular coordinate system. We're going to talk about how to analyze vectors in space. And then we're going to set up 3-dimensional vectors to solve problems. The way that we set up coordinates in space is a little bit tricky, but it's not too bad. So coordinates in space, we have an xy plane. Think of this as the surface of your desk. So x, y, and then sort of coming out of the surface of your desk would be the z-axis. The desk surface would be called the xy plane. The horizontal line with the vertical out of the desk line would be the xz plane. The out of the desk line, z, with the sort of up and down on your desk line would be the yz plane. To model this for you, I would suggest sort of drawing on your paper just a typical xy axis. This is the basis of 3-dimensional space. So x, y, x to the right, y up, and then negative y down, negative x to the left. The z-axis would come out right here, straight up out of the paper. There's a symbol that you often see in engineering that might be helpful here. The z-axis would be a little circle with a dot in the middle. This would be indicating the z-axis coming straight out of the paper right here. This would be positive z vector coming straight out of the paper. Contrast that to the negative z, which would look like a little x in a circle. It's not the X-Men symbol. This would be negative z. What this is this is it's kind of a funny symbol, but it's like an arrow with a little cone on the front, and then a shaft, and then sort of the feathered end coming out. This is the sort of vector arrow for z. So if you imagine you're looking at this arrow coming straight out, that's why it looks like a little dot with a circle around it, because you can tell the little cone there. If it goes down, you're only seeing the sort of back of the cone and little crisscross of the feathers on the end of the arrow there. So that's what that looks like. So x-axis, y-axis, and then z-axis straight out of the paper towards you. We're going to be working on what's called a right-handed system, or as contrasted to what's called a left-handed system. In the right-handed system, if you were to stand up straight, the z-axis would be up and down throughout your body. Your x-axis would be represented by your right hand, and if you hold it at a 90-degree angle, the y-axis would be represented by your left hand. The left-handed system would switch the two hand axes, so x would be to the left, y to the right, and z would be straight up. Almost for sure, everything that you do in at least undergraduate mathematics will be right-handed systems. I've never actually encountered anyone using a left-handed system for any practical purpose here. So right-handed systems, x, y, and then z straight up and down. A lot of the work that we did with two-dimensional vectors can be applied here. So for example, we can use the distance formula, but instead of being in 2 dimensions, we can use it in 3 dimensions. This is something you maybe did in geometry, at least your geometry teacher should have told you about. In 3 dimensions, the distance formula looks exactly the same, x2 minus x1 squared plus y2 minus y1 squared, and then we just add in the z components, z2 minus z1 squared. This is very useful for the magnitude calculations we're going to be doing in a little while. The work that we did in 11.1 is almost the same as the work in 11.2. So let's practice this. We're going to find the distance between 2 points, 2, negative 1, 3, and 1, 0, 2. So if I'm going to set up the distance formula here, that would be the square root of, okay, so this one minus this one, 2 minus 1 squared plus this one minus this one, negative 1 minus 0 squared plus this one minus this one, 3 minus negative 2 quantity squared. And what we end up here is the square root of 2 minus 1 is 1 squared plus negative 1 squared, which is 1, plus 3 minus negative 2 is 5. 5 squared is 25. And so the distance between those 2 points is equal to the square root of 27, which we could reduce to 27 is 9 times 3, so that would be 3 root 3. Little review from geometry. Now the distance formula comes in handy not just with vectors, but you can also do things like 3-dimensional space. So like for a sphere, very similar to a circle, a sphere with the center at x naught, y naught, z naught, and some radius r would have a formula that would use the distance formula to calculate that r value in 3 dimensions. So very similar to the circle formula in 2 dimensions, it's x minus x naught squared plus y minus y naught squared plus, writing in the 3rd dimension, z minus z naught squared, is equal to that distance formula r squared for the 3 dimensions. The midpoint for a sphere would be similar to the midpoint of a circle. Take the 2x components, divide by 2. 2y components, divide by 2. 2z components, divide by 2. Very useful. If you do a real quick calculation, let's pretend like in the last example, this was the center of our sphere, and this was a point on the edge. What would the equation for this sphere be? Well, it would be x minus, if this is the center, the x minus 2 squared plus, if this is the center, it would be negative 1, would be the y, so it would be y minus negative 1, which would be plus 1, squared plus, this is my z1, or z0, I should say, this would be z plus 3 squared, and then that's equal to 3 square root of 3 squared, which would be 27. That would be the equation of the sphere with the center point 2, negative 1, 3, and a point on the outside 1, 0, negative 2. So let's talk about some of the properties of vectors in space. Almost exactly the same as the notation for 2-dimensional vectors. If we have some vector v, which is composed in the component form of v1, v2, v3, the non-zero vector, the zero vector is composed of 0 is equal to, instead of 2, we have 3 spots for that. Unit vectors I and j are the same as in last lesson, but the k vector is 0, 0, 1 in the positive z-axis. So the standard unit vector notation becomes v1i plus v2j plus v3k. The equations for vectors in 3-dimensional space are almost the exact same as for 2-dimensional space. So equality of vectors is still true if u is equal to v, if the components u1, v1, v2, v2, and u3, v3 are the same. We also have the length, or the magnitude of the vector, being almost exactly the same, but it's v1 plus v2 plus v3, each of those terms squared. This time, the unit vector in 3-dimensional space is just the same as in 2-dimensional, with that added component of having the v3 there. So you use the magnitude calculation first, and then you divide each component by that by that magnitude of v. Vector addition is the same, except instead of just x and y, it's also x, y, and z. Same thing for scalar multiplication. It's c times each component in x, y, and z. Okay, so let's try to use this. We're going to find the component form and the magnitude of the vector v having initial point, negative 2, 3, 1, and a terminal point, which is the end point, 0, negative 4, 4. And we're going to find a unit vector in the direction of that v. So to find that, we're going to set up v is equal to, so this is my initial, this is my final. So 0 minus negative 2, and we'll do this in this component form here. That'll be the x terms, then it's going to be negative 4 minus 3, and then it's going to be 4 minus 1. So in component form, what we get is that v is equal to 2, negative 7, 3. This is, I just want to remind you again, exactly the same as 2i hat minus 7j hat plus 3k hat. This is the first time you're seeing k hat, but it's just the lowercase k with a little arrow on top. Now we want to find a unit vector in the direction of v. So to do that, first I need to calculate the magnitude. Magnitude of v is going to be equal to, and we'll use that three-dimensional distance formula. So I don't need to start with this point minus point because I already know the values of those, that they're here. 2, negative 7, 3. So I'm going to do 2 squared plus negative 7 squared plus 3 squared. 2 squared is 4. Negative 7 squared is 49. And 3 squared is 9. You should always get a positive number because you're squaring each of these terms. You should always get a positive number for the magnitude. 4 plus 49 is 53, plus 9 is 62 square roots. That's our magnitude for v. Now if I want to find the unit vector, remember I said earlier, I use that u in reserve, so the unit vector for v here is equal to 1 over the magnitude, so 1 over root 62, times the component form of the vector, 2, negative 7, 3. I can expand this by multiplying through by the scalar, so the unit direction vector would be 2 over root 62, comma, negative 7 over root 62, comma, 3 over root 62. Now if root 62 could be simplified, we should probably do that, but in this case 62 is not. It's 2 times 31, and both of those are prime. So we'd say that two vectors would be parallel. We're introducing this concept. Two vectors are parallel in 3 dimensions if they have equivalent values or some scalar multiple of the values. So u could equal v, or u could be equal to some scalar multiple of v itself. As an example here, u is parallel to v. This is a 2-dimensional example. U is parallel to v. They never meet. They always run next to each other. V is also parallel to w, but they're going in opposite directions. That doesn't matter. They're still parallel to each other. The negative sign is just a scalar multiple of 1. And because u is parallel to v and v is parallel to w, u is parallel to w. That's a proof from way back in geometry. So to finish up for this lesson, let's try to actually do this. If we say vector w has an initial point, 2, negative 1, 3, and a terminal point, negative 4, 7, 5, which of these two vectors is parallel to w? So let's first calculate w. W vector is equal to in component form. And as you start to do this, you can do a little less work here. So vector W is equal to, okay, so terminal point minus initial point, so -4 minus 2 would be -6. Terminal point 7 minus -1, which would be 8. Terminal point 5 minus 3, which would be 2. That gives us W. Now, I'm going to compare this to this. W can be a multiple of this, so I'm going to look at U first. So 3, -4, -1 looks very similar to this, right? Except I notice the signs are changed. This is positive, this is negative, this is negative, this is positive, this is negative, this is positive. And then this is being multiplied by a factor of 2. So if I multiply -1 times the U vector, or not -1, let's just go -2. If I multiply the U vector by -2, I would get 2 times 3 would be -6. 2 times -4 would be 8. And -2 times -1 would be 2, which would be equal to W. So I can write that W is definitely parallel, in the same symbol from way back in geometry. W is definitely parallel to U. Checked, verified. Okay, let's try V. V looks promising as well. V looks about twice the size of W. So if I multiply V by, let's say, 1/2, and then I notice the signs are kind of changing there. So we'll go -1/2, so -1/2 times V would be equal to -1/2 times 12 would be -6. -1/2 times 16 would be +8. And then -1/2 times 4 would be -2. Now I notice this is the same, but I need to do all 3 steps because these are not the same. So V is not parallel to, sometimes write like this, not parallel to W. So W is parallel to V is the final answer. And that concludes this lesson. Those are the homework problems that I would advise you to check out. And then again, make sure you're doing the reading. Thanks.